Win game, win money. Devil's Plan, Netflix's #1 game show, paid the winner $300,000. But instead of testing physical strength or cooking skills, Devil's Plan tests your mind. Board games, card games, deception games. But today's question is, could we win Devil's Plan? And the answer is yes. With some help. Wall Go is a game where you and your opponent fight for space on a board. Each turn, you select one of your pieces, move it 0, 1, or 2 spaces, and place a wall adjacent to your piece. The game ends when no space is contested, and the winner is the player who ends with more space. So let's solve Wall Go. The first approach we will use is Minimax, which means you make the best move, and you assume your opponent makes the best move. In 3 in a row, the most popular strategy is Minimax. The strongest move for O is to block, because if left open, we assume next turn X will take the win. We implement Minimax by giving each board an evaluation. +1 is completely winning for white, and -1 is completely winning for black. As white, we choose the most positive board state, and as black, we choose the most negative one. Minimax is accurate but expensive. At depth 1, computer thinks one move ahead. For each legal move, we evaluate the candidate game state and select the line with the most positive outcome. For each additional depth, we compute an additional 104 game states per game state. Computing the entire game with Minimax requires depth 40, which is about 10 to the 80 game states. This number is so large, there are more atoms on Earth than game states. We need another approach. A neural network predicts an output from an input state using previously trained data. For our neural net, the input is a board and the output is the evaluation. On this board, our neural net could predict +0.2, which means slightly winning for white. Or, on this board, a prediction of -0.9 means extremely winning for black. Let's use a hybrid approach. Use Minimax at small depth, let's say depth 3. Computer evaluates 3 moves ahead, choosing lines that are completely winning and avoiding those that are completely losing. If unclear, computer falls back on the neural net to predict the evaluation, then chooses the line with the strongest evaluation. This works in theory, but we have a big problem. For a neural net to accurately evaluate a game state, we need lots of training data. And unfortunately, we have none. Wall Go was created for the show Devil's Plan. So with no public database of games played, our only option is to build our own.
Tip number 10. Sit at the chessboard and play with yourself. It's amazing.
Our model trains against itself. Reinforcement learning means during play, we penalize losing lines. Over time, our model learns the ability to determine winning lines from losing ones. In Wall Go, when white wins, we know the last board has a +1 evaluation, completely won for white. But how did we get to +1 from the neutral starting board, which evaluates to 0? Well, we can fairly say, somewhere in the game, black made some mistakes. Let's assign gradient evaluations for each board state. By itself, this does not accurately describe a game. It is very rare that black would make one small mistake each move. Most games have some good moves, some bad moves, and some in between. Our hope is that in aggregate, over thousands of games, gradient evaluations could accurately describe a board state. If in 1,000 games from a single board state, white ends up winning 950, we can estimate that this board is pretty winning for white. Let's package these games as training data to feed back into our neural net. So, let's try it out. While we sleep, computer plays 10,000 games against itself. And the result is disappointing. We beat the computer easily. As if computer learned nothing from its training, it moves pretty randomly and even sometimes traps its own pieces. But hope is not lost. Let's make some improvements. If computer only selects what it believes is the best move, it might miss out on a quieter but even better move. At some small epsilon, let's say 1% of the time, computer will select a random move. If this random move is actually a stronger move, over time, our new move will lead to more wins. During training, our neural net will eventually favor this new, better move. Currently, our neural network trains from the vector representation of our board. This consists of whose turn it is, piece positions, and wall positions. Let's add columns for the percentage of space claimed. Contested, white, black, and none. These values reveal a lot of information for how the game is going. This is because exactly one space claimed means your piece is trapped. In a 1v2, your position is almost always losing. With these new tools, let's give it a week and let the computer play 100,000 games. And the result is a Wallgo master. We lose to the computer quickly and methodically, but it's time to test the computer against a worthy opponent. Rob is good at games. Can Rob beat a computer that's trained 100,000 games? Well, computer takes the win. After working so hard, day and night, you deserve a rest. Until next time.